might be handy just to revise index laws. You would have covered these last year in Year 9, and I know that because my current Year 9 extension class are doing them, and the year before that my Year 9 class did them then, so I don't need a proof to deduce that you guys have covered these. Okay, and maybe a couple of others as well. So pause it if you just want to refresh your memory. You've also seen these in a previous PowerPoint. If not, let's move on. Here's an example of proof by induction. We're required to prove that AB raised to the n equals A to the n times B to the n. N being natural numbers. Okay, so we need to try a base case. Base case is when we try n equals 1, and usually it's n equals 1. In this case it definitely is, and we want to see if the first domino falls. So base case, try for n equals 1. What we have, one way of doing this is LHS means left hand side, RHS means right hand side. It's a common thing we do in mathematical proofs. I'm going to use that here. So left hand side, i.e. this side, left hand side then equals, if we're trying n equals 1, A times B to the power 1. Now we know that equals AB. Right hand side for n equals 1, that's being the right hand side, A to the 1 times B to the 1, which equals AB. So yes, it's therefore true for the base case. Okay, so we've shown that yes, that first domino has fallen. Okay. Now we look at the inductive hypothesis. We need to assume it's true for some domino picked at random. I wonder if I should experiment with some colour. So I'm learning as I go. I wonder if that will make it a little bit easier to follow. We'll see. I'm sure you'll tell me. So assuming it's true for some value n equals k, that's that random domino. So this is the inductive hypothesis. Okay, hypothesis being a testable statement. You remember from the last video? Of course you do. Okay, so assuming it is true for n equals k, that's that inductive hypothesis, some domino k. Okay, chosen at, it's like being chosen at random. We would have, based on our original, up here, can you see? Based on our original premise, okay, if n equals k, we would have a b to the k, amazingly enough, equals a to the k times b to the k. Now we're going to use that again, so I'm just going to call that statement 1 or equation 1. Alright, so we'll leave statement 1 there for a minute. We must also show the inductive step. This is if some random domino is chosen. If it happens to fall over, then the next one will, and all the dominoes are equally spaced, and all the dominoes represent a bunch of statements. If k falls over, we must also show that k plus 1 falls over. So if k holds, the case of k plus 1, the inductive step holds. So inductive step, where n equals k plus 1. We're going to try and show that now. So that would be, in terms of our premise up here, there, our original premise, our hypothesis, we're looking at we need to show that we must show that, not a proper W, Mr. Herbert, AB to the k plus 1 equals A to the k plus 1 times B to the k plus 1. And we haven't shown that, that's what we've got to show. So we've got to see if that will work. Alright, so how do we do it? That's the big thing. Often that's the hardest part of an inductive proof. Alright, so this is where the mathematical creativity comes in, and creativity is higher order thinking, and if anything's going to be difficult in one of these things, this is the step. Now if we multiply both sides of something by the same thing, we know that both sides, if they're initially equal, they will remain equal, and that's an axiom, isn't it? So I need to become more fluent at this, don't I? So axiom, we're going to employ an axiom. Okay, so we're going to multiply both sides by AB. Okay, you don't actually have to write that yellow bit down, but that's what we're doing. Where was I? Alright. Maybe we should change colours again, hey? Well, it's either a good thing or a bad thing. So here's the inductive step in action, going from k through to k plus 1. It's a process, okay? So if we multiply using 1 above, statement 1, there, alright. If we multiply both sides by AB, we'll have AB to the k times AB. We will have on the right hand side A to the k, B to the k times AB. And what we have here is, on the left hand side, if we work on that, we basically have A, B to the k times AB to the 1, don't we? Now when we are multiplying something to a power, for base to a power, and we multiply it by another factor of that base, it goes up by 1. Have a think. Have a think about that. You don't need to, you can reason that directly. You don't need any particular rules. If you had, for example, 2 cubed times by 2, alright, without even worrying about index laws, you know that that's going to be another factor of 2 in there, okay, and that's going to be 2 to the 4, isn't it? Okay, so this is not something you would write into the proof. This is just a bit of reasoning, isn't it? I'm just checking that you realise that, because we're timesing by another factor of 2 in there. Okay, so trying to make sure this video doesn't go forever. It's going to chew up a lot of data if it does. So here we go. We've got AB to the k times AB. In other words, we're timing both sides by AB. On this side here, left side, we'll have AB to the k plus 1. Doing the same thing to the right. That's going back to this spot right there. Okay. Okay, we are looking at splitting these up because it's an axiom that commutativity works. Okay, so we can change the order of these products. Yeah. And just like over here, once again, you multiply these, it goes up by 1. Remember that, the index power goes up by 1. Same reason as I said just before. That would mean that here and here we see a to the k will go up by 1. Well, what's k with 1 more onto that? K plus 1. And what's b to the k plus 1 more is b to the k plus 1. Okay, so we have shown that by multiplying both sides by the same thing, we can do that. It's an axiom. We can go from this step to the inductive step, from the inductive hypothesis to the inductive step, and it holds. So we have shown that since it's true for the base case, and since it's true for colour, I'm going to work my colour schemes out a bit better. Let's get some closure. We start in red, we'll end at red. Since base case is true, and if n equals k, the hypothesis, if n equals k is true, whenever n equals k is true, n equals k is also true. We've shown by induction that ab to the n, okay, ab to the n equals a to the n, b to the n. We'll practice that in class more next week. Main thing is that you've watched both of these videos and you've had a good think about it, and maybe if you're keen, try a couple of those activities again. Thank you.